This conference will now be recorded.
Yeah, just a minute. My screen is coming. Hmm. So today we'll be discussing LC oscillation. So far we have learned if we apply AC signal, AC signal to the individual inductor circuit, capacitor circuit, or purely resistive circuit. So in those cases we have calculated the current. So we have learned what is the phase difference between the current and voltage in individual circuits. Then we had learned LCR circuits. We have seen there is oscillation and resonance happens in LCR circuits. So those things we have learned. So today we'll be learning LC oscillations. So what is this LC oscillations? So when a capacitor which is initially fully charged is connected to an inductor coil, the charge in the capacitor and the current in the circuit exhibits an oscillation that is called electrical oscillation or electric oscillation, which is exactly similar to the exactly similar to the oscillations observed in the in case of mechanical system, for example spring mass system or spring block systems. Okay, I'll explain what is written over here. Suppose there is a capacitor, as you can see here, which is when a capacitor is fully charged, so in the both plates the charges will be equal in amount but opposite in nature, and at the same time there will be a potential difference between these two plates. Okay, if you charge this capacitor with a DC battery, then we have learned in the previous classes that if the voltage of this battery is V, after this capacitor gets fully charged, the potential difference across the plates will be exactly equal to the battery voltage, that is V. Now what happens if you use this fully charged battery charged capacitor, since it has potential differences between these two plates or terminals, so that is V here, then what will happen if you connect this with a circuit, it will start flowing current in the circuit. So in this case you look, a fully charged capacitor is connected in series with this inductor coil. Okay, and there is no battery. If you look, there is no battery or signal generator, signal generator. generator or AC source. There is no source in this circuit. Okay. So as I mentioned, a fully charged capacitor can act as a battery. It can act as a battery. Okay. Why? Because fully charged capacitor has potential difference, and if the both the terminals are connected to this inductor, then this capacitor will start discharging. That means if there was suppose capital Q charge initially, then it will discharge by some small amount delta Q after some time. Again, it will charge maybe delta 2 delta Q. Like that, it will discharge, and that charge will be flowing in the circuit. So flow of charge means current, right? So what does this mean? This means that a fully charged capacitor can act as a battery which can flow a current in a closed circuit. Okay, like this what you see over here. Since only there are two components, electrical component, one is C, another one is L. That's why this circuit is called LC circuit. LC circuit. This is C capacitor, and this is L for inductor or self inductance. Okay. So but there is no battery, right? There is no battery. So no external source over here. So what will happen, you know, according to the conservation of energy, if there is no dissipation in this circuit, no dissipation of the energy, ideally what happens? So this charge in the capacitor will be reducing or discharging. The capacitor will discharge, and during that process the capacitor will send a current through the circuit. And when a current flowing in the inductor, and if that current varies, you look here, initially suppose it was 100 microcoulomb charge when it was fully charged. Now if after 5 seconds it loses some, or it gets discharged, okay, and now the charge is some 95 microcoulomb, okay, then at each instant, since it is getting discharged, since the capacitor is getting discharged, so the current will not be a constant current. So at each instant the capacitor is losing some charge, right? Some charges. So current in the circuit cannot be a constant current. Constant current, okay? It will be a varying current, constant quantity, I can say. So the current also changes with time, and as you know, when a time varying current is flowing through an inductor, what happens? There will be induced EMF in the inductor, and that can be written as minus L di dt according to the self inductance or self induction. So this we have already learned in the previous chapter. Self induction, when a current flowing in the inductor coil excuse me, is varying with time, the inductor coil in the inductor coil there will be an induced EMF which is given by minus L di dt. Okay, and you can see the polarity will be exactly opposite to the capacitor. Look, here it is positive, here it is negative. It is opposite polarity. It has opposite polarity, right? So this induced EMF will actually see when this change in the current is maximum, then the induced EMF also will be maximum. Okay. All right. So what I mean to say is that this capacitor initially when it was charged, fully charged, it was holding a certain electrical energy that is called electrostatic energy. So that is actually given by q square by 2c. If the maximum charge in the capacitor initially qm, then it is qm square by 2c. So when it is getting discharged, so it is losing its energy. At the same time, if there is no dissipation of the energy, the same energy is getting stored as magnetic energy in this inductor. So how to write that magnetic energy? Half L I square. So that depends on the current. If the current is maximum in the circuit, then the magnetic energy stored in the inductor also will be maximum. So you know the energy will be oscillating between capacitor and inductor. Or in another way, I can say the charge will be oscillating. Charge and current in the circuit will be oscillating here. How? Initially capacitor will be fully charged, then it will start discharging and sending current through the circuit, and by that process when current is changing through the inductor coil, it will induce an EMF, and the electrical energy which is actually released by the capacitor will be stored by inductor as magnetic energy. When this capacitor is fully discharged, that means charge is zero after certain time interval, the whole charge in the capacitor will be zero, then there will be no electrostatic energy stored in this capacitor. The whole energy will be getting converted to magnetic energy, that I can say maximum kinetic energy half. So sorry, magnetic energy half L I m square. When the current in the circuit is maximum but charge in the capacitor is zero or minimum. Okay. So when this gets totally discharged, the inductor will start flowing current through the capacitor in the circuit. So first the capacitor was flowing current because it was fully charged, but there was no magnetic energy stored in the inductor coil in the beginning. Okay. So now when the capacitor is fully discharged, the inductor will start flowing current through this capacitor in the circuit. So what will happen? The capacitor will slowly develop charges again, and it will see the inductor will be thereby losing its magnetic energy, whereas the capacitor will be storing electrical energy, like the same energy in the form of electrical energy, and thereby when again the capacitor will regain its whole charge but in opposite polarity, then the whole magnetic energy again will be converted to electrical energy. So you can see the mutual conversion of energy happens in this circuit, or I can say the energy oscillates between magnetic energy and capacitor. electrostatic energy, or what we know, the charge is oscillating or current is oscillating in the circuit. So that's why it is called electrical oscillations. And this oscillation is very much comparable with the mechanical systems. We'll be taking a simple harmonic motion of a spring mass system. Whenever we talk about oscillations, we always compare with simple harmonic motion to find out the oscillations and other parameters for that oscillations. And wherever there is an oscillation for practical instruments or anywhere, we will try to bring the approximation up to simple harmonic motion, and then we will compare to find out various physical parameters. So that is done in many places in physics. You may learn when you go for higher studies again. So in summary, what I'm trying to do now, we'll see, we'll try to set up an equation of motion for oscillation of this electrical circuit, LC circuit. So we have to find out equation of motion. So aim is to find out equation of motion, EOM, in abbreviation, equation of motion. Okay, I'll write the full equation of motion. And then what we'll do, we'll compare with spring block or spring mass system. Then we'll find out some analogy between the electrical and mechanical quantities. Analogy between electrical and mechanical quantities. Mechanical quantities in the sense physical and mechanical parameters, I'll say parameters or quantities. Okay, or quantities. So what is the aim for today's class to learn? So there are few things which we will be doing here. We'll first apply Kirchhoff's voltage law or loop rule to find out the equation of motion, and we'll compare the equation of motion with the mechanical equation of motion for simple harmonic motion, especially with the spring block system. And then we'll see how the oscillation in LC circuit can be visualized and compared with this mechanical system. And we'll try to find out some analogies between the electrical quantities which are involved in this oscillation with the mechanical quantities or parameters which are involved in simple harmonic motion in case of mechanical system. Okay, I'll just erase this. Now look, by Kirchhoff's law, Kirchhoff's loop rule or KVL, it is called Kirchhoff's voltage law. By Kirchhoff's voltage law, we can write down the equation. Here is Q by C. This is this is equal to minus is equal to L di dt. So if I bring both in the left hand side, so it will be, this is the equation I can get if I apply Kirchhoff's voltage law or rule. Now look, in this case, what is happening? Q is reducing. Okay, Q is reducing, and I is increasing. Okay, so these two parameters will be actually oppositely changing with time. One is increasing, another one is decreasing. So look what I can do. I can write I is equal to minus dq dt. This I can write because current will be increasing if the charge decreases in the capacitor. Okay, so if I write this in terms of q, if I write this equation in terms of q, so that we can find out a solution, or maybe we can set up a proper equation which can be very much equivalent to the equation for simple harmonic motion in mechanical system. Let us see. So this is q by c. I'll keep as it is. So this is L di dt, that means ddt of dq dt with a minus sign. Okay, hope you are understanding this. Now this minus sign will make the whole as positive, and this can be written as d2q by dt square. This is equal to 0. Look, I'll just write it like this. Is equal to 0. Okay, I'll just erase this front part and I'll keep the equation. So maybe I'll just repeat it what we have done. So we have just written down the Kirchhoff's voltage law for this circuit. See, in this case there is no battery, right? Whatever voltage drop across this is there will be exactly equal in this inductor, across the inductor. So you can just simply write q by c is equal to L di dt. Drop across inductor will be exactly equal to the voltage across the capacitor itself. Okay, so this is the equation of motion, sorry, equation we have written down. Now see, I know here the charge is reducing and current is increasing, so they are oppositely changing. I can write I is equal to minus dq dt, and if I want to replace this I in terms of q, then see I have done it here, this line, then I have just simplified it. Okay, so what I have got is this equation. So this is the final equation I have got for this circuit. I'll just erase everything and I'll write the final equation what we have got here. Plus q by c is equal to 0. Okay, look, this equation is very much familiar to us. If you remember, the oscillations or simple harmonic oscillations, in case of a simple harmonic oscillator, what was the equation of motion in case of mechanical system? We know if x is the displacement and omega is the frequency of oscillation of that mechanical system, we can write it down like this: d2x by dt square is equal to omega square x is equal to 0. Look, this is the familiar and well-known equation for simple harmonic oscillation. Okay, so this is well-known equation for simple harmonic oscillation, SHM, for, okay, so equation of SHM for a mechanical system. This you have already learned in your 11th standard. We are going to use this equation here just to compare what we have got. Just compare these equations. See, these equations are having the similar form. So can I say that LC circuit exhibits oscillations if I compare these two equations? Yes. If we compare these two equations, then we can say that LC circuit exhibits electric oscillations similar to the simple harmonic oscillation that is observed in case of mechanical system. Okay? So that's why the topic is LC oscillation. When you have L and C together, if the capacitor is initially fully charged, then charge in the capacitor and current in the circuit will oscillate, and that oscillation will be a simple harmonic oscillation and very similar to the mechanical oscillations observed in case of, maybe you can think of spring mass system or simple pendulum or whatever. So if we now compare these two equations, see, we may be able to find out few analogies over here. Okay, so like, see, the displacement is equivalent to the charge in the capacitor. Okay, all right, few more things we'll be learning with the analogy part. We'll just come that later. But now again, what we'll see, we'll just see the comparison of electrical oscillations with the oscillations of a spring mass system. We'll just take a spring block system. See what I'm doing here. I'm just I'll just make you recap what is spring block system. Suppose you have a block of mass m attached to an end of a spring, and the other end of the spring is attached to a fixed wall. Now see, the spring, suppose this is the normal configuration or the natural configuration or natural length of the spring. Now if you hold this block and pull it this way, then what happens, the spring will be getting stretched. Okay, getting stretched. Suppose this was the original position or equilibrium. Now you have stretched it by some distance x. Okay, some distance x. Obviously I should have done symmetrical. Anyway, let us see. So this may be another side. So this side is x again. I'd say here this is minus x, this is plus x. Suppose this is the equilibrium position O. So if you pull it this side, the spring is stretched. So what will happen due to, so if it is stretched within the elastic limit, the spring will actually give a force. See, you are giving certain force in this direction. So the spring also will give you restoring force such that the spring is able to bring its configuration back to its original configuration. So that force is called restoring force. So which can be written as F is equal to minus Kx. K is the spring constant, and see, this force is called spring force. Spring force. It is always opposing the or in the opposite direction of the displacement. If you displace in this way, the spring force will be in this way. Okay, if you displace, or if you just, this is stretching, suppose. Now if you compress in this way, the spring compress this way, the spring force again it will be against the compression. Okay, so spring force will be always opposing the external force which is changing its configuration, whether it is stretching or compressing, it will oppose that compression or stretching. So if this happens in the elastic limit, what happens? If you just pull it like this and just leave it, what will this spring mass system will do? It will come back from here as you leave it here. So it will come back to its equilibrium position, but it will not stop because of inertia. It will go up to the minus x distance again. This, so this is called displacement. So this mass will go in the opposite direction, also same amplitude. This is amplitude or same distance, where its energy will be, or kinetic energy will be lost, and then it will come back again towards the equilibrium, but it will not stop here again. If there is no opposing force or friction or any other damping, it will go back to again or the initial position here. If I say this is A, this is O, this is B, so it will, if you just leave from A, it will go to O, then it will not stop, it will go to the next side, like opposite side up to B, then again it will come back from B to O and O to A. So this is what it will continue. If that, so if this is an ideal situation, there is no damping, no resisting force, then this oscillation, so this will oscillate mass, this block will oscillate back and forth, and this oscillation will go on for infinite time if it is the ideal situation, but in reality there will be a time when it stops because of various damping forces. So this is actually the simple harmonic motion which this block will execute. So this spring mass system, this is called spring mass system or spring block system. Very important and well known and very simple model of simple harmonic oscillation. Okay, so here we'll be comparing our LC oscillation with this spring block oscillation. Okay, so let us see here. So when the capacitor, so I think you are just able to see this figure. So this is again taken from your NCERT textbook itself, just for your demonstration. See, when the capacitor is fully charged and it is connected to the inductor, but circuit is not yet closed, so this is open still. So at that situation, as I said, the fully charged capacitor will store an electrical energy which is given by q square by 2c. So this is the electrical energy which is stored in the capacitor. Now as soon as you close the circuit, what happens? As I said earlier also, it will start flowing current in the circuit. Okay, then no longer the capacitor will hold the whole energy. So the energy will be distributed, some energy will be distributed to the inductor also. How? As I said, when the capacitor start discharging after closing the circuit, there will be a current developing in the circuit. If there is current, and that current, as I explained how it changes, the current changes through the inductor coil, then there will be an induced EMF and magnetic energy will be stored. So the energy this capacitor will release, or electrical energy which will be lost, from the capacitor will be converted to magnetic energy and stored in the inductor coil. So look this configuration. So see, this is compared to the spring block system when it is stretched. So in the beginning it is stretched. Stretched means, so suppose this is the A condition what I explained just few minutes back. This is the equilibrium position O. Now it is at A, that means it is completely stretched condition. At this condition, this mechanical system will be holding the maximum potential energy. You can see this U is equal to half K A square. A means the amplitude, maximum amplitude. If this is A, then it is the K A square. So this is the energy stored by spring. This is potential energy which a spring. So you may remember that a spring can store a potential energy. That potential energy can be written as U is equal to, suppose USP minus half K x square. Okay. So if you take the modulus of that, so this will be half K x square at any instant. Okay, at any instant of its oscillation or at any displacement. This is the general displacement. But if it is maximum displacement, suppose A, then this energy will be A square. Okay, so this is the maximum energy, electrical energy, which a spring mass system can hold. This is the mechanical energy, mechanical potential energy. But in this case, in the LC circuit, when the circuit is not closed, but the capacitor is fully charged, then capacitor will hold the whole electrical energy as potential energy, electric potential energy Q square by 2C. Okay, so QM actually is the maximum charge in the capacitor in the beginning, suppose in C. Okay, so this is compared to stretched condition of this spring block system. Now as you release here, as you connect the circuit or close the circuit, that means you are just releasing this block from its maximum stretched condition. Look, this situation is the second case. So as I said, when current start flowing, there will be both the energy, and see, there will be electric energy, there will be magnetic energy, and as a whole this energy will be the total energy which was earlier when the capacitor was not connected to inductor. That means, see, at any situation, in this case when the current is flowing in the circuit, so there will be magnetic energy as well as the electric energy, and as a whole, if you take the sum of those two, energy will be equal to this qm square by 2c, which was in the beginning. So this will be the sum of these two energies at any instant of time. Okay, after the circuit is closed. Now in this case, you look the mechanical system you have already released. That means when you release, the block will actually move towards the equilibrium. Okay, towards A. So it will actually gain a kinetic energy. It will gain some kinetic energy because there is a velocity, so half mv square. So you look here, there will be both kinetic energy and potential energy non-zero. That's why it is written u not equal to 0, k not equal to 0. That means the kinetic energy as well as the potential energy both will be there in this system now because it is moving. So what will happen actually in this spring mass system? It will lose its potential energy as it goes towards the equilibrium situation and gain more and more kinetic energy. Similar to this, in the LC oscillation also, when time passes, charge will be reducing in the capacitor and current will be increasing in the circuit. So electrical energy will be converted to more and more magnetic energy and stored in the inductor coil. Okay, so this is the second situation. Now come back to the third situation. So if I take this solution for this equation, d2q by dt square is equal to omega 0 q is equal to 0. If I suppose the solution for this is qm sine omega t, okay, suppose phase angle 0. So if this is the solution of this equation, then charge is oscillating as a sine curve. It is like, so in the beginning it will be 0. So this is actually oscillating as sine curve, and the current is oscillating. So current will be oscillating as your cosine curve. Okay, but both are supposed in the same phase. So it will be something like this. Okay, so uh, like this. Okay, so this will be the cosine curve. If you take derivative, time derivative of this, so you'll get, okay, I'll just do it. I will be qm into omega 0, omega 0, then cos of omega 0 into t. Okay, this is the current. Both charge and current suppose are in same phase. Okay, so they will oscillate like this. So this is current and this is the charge oscillating. Look, charge is reducing and the current is increasing, and see when it is, so t is equal to t by 4, that time the charge, sorry, current will be maximum. Okay, current will be maximum in the circuit, and that maximum current will be this one. So this is actually for mechanical system. It is the equilibrium situation when the part, this block is exactly at the equilibrium situation or position, or when it is crossing the equilibrium position, the velocity of this block will be maximum at this equilibrium. Okay, so at this situation the whole energy will be the kinetic energy, and energy will be 0 over here, because the kinetic energy is maximum and whole energy will be half m v max square over here at this equilibrium. Same situation over here when the capacitor is fully charged. See, there is no charge over here, then the current is maximum in the circuit. So since there is no charge, so there will be no electric potential energy stored in the capacitor, so it is 0. So the whole energy will be magnetic energy, and that is given by half L I m square, maximum current in the circuit. So you can see the analogy is very coherent and very interesting, right? So this is up to this. So this is up to t by 4 when the current is becoming maximum in the circuit. Now situation will change. See, so here the capacitor was fully discharged. Now the current is flowing in the circuit by the inductor. So what will happen? See, mechanical. See this magnetic energy now, which was stored in the inductor, will be now reducing or spent. That magnetic energy will be spent in sending the current through the capacitor in the circuit. Now, so in this case, what will happen? Since the polarity was opposite, so here it's positive, here negative. So what will happen? So the capacitor will be again collecting charges because of the flow of the current in the circuit by inductor, But this time you can see slowly it is charging, but the polarity is opposite. See, in the beginning polarity was negative, here positive. Now it is here positive and here it is negative. The polarity changes. As you can see in the mechanical system also, when it just crossed the equilibrium situation or equilibrium position, the displacement is in the opposite direction. Suppose this is the positive x direction, now it is in the negative. So this is origin, now it is going in the negative x direction. Okay, so this displacement is opposite now. And you can see at any intermediate situation just after crossing the equilibrium, there will be both the energies, potential energy as well as the kinetic energy. Both energies will be there. As you can see here also in the C, charge has been stored somewhat. So there will be some electric energy and there will be magnetic energy as well. So the total energy will be given by the sum of these two. Okay, hope you are understanding. Now see, if time passes, then what happens with time? The capacitor will be collecting more and more charges, and eventually it will be fully charged at certain point of time. At that time what will happen? The whole energy will be converted to again electrostatic energy qm square by 2c. Okay, and magnetic energy, as you can see, there is no magnetic energy stored further in this inductor. Okay, so b magnetic energy will be 0. The whole energy again becoming the electrical energy, electrostatic energy, which is stored in the capacitor. You look here in the mechanical system, the block is now compressing the spring, and that is the maximum amplitude in the opposite direction. So the whole energy at this particular configuration will be the potential energy, which is half k a square, stored in the spring. And at this position velocity is 0, so there will be no mechanical kinetic energy at this particular configuration when it is having maximum amplitude in the opposite direction from the equilibrium situation. So this is how you can see, this is now the polarity of the charge is opposite. Now again what will happen? Again the capacitor will start flowing current, but now current will be in the opposite direction. So after this situation, as time passes, the capacitor will start flowing current again. So that time the induced EMF will be here positive, here negative in the inductor. Okay, so again magnetic energy will be stored in this inductor and capacitor will be discharging, and finally it will be becoming in the intermediate situation, it will be fully discharged and then charged by the current sent by this inductor again, and it will come back to its original position, like original condition when it was fully charged with this polarity, having positive here, positive here, negative here. So which is the initial situation. So it will continue like this, and as you can see, the energy is getting oscillate. It is just oscillating from magnetic energy to electrical energy, and charge is oscillating from minimum to maximum. Okay, at the same time current also in the LC electric circuit, it is just oscillating from minimum to maximum. So this is why it is called LC oscillation. Okay, so this is whole thing about oscillations, LC oscillations, and you can see both the charge and current oscillates in the circuit. Also the energy oscillates between inductor and magnetic energy and electrical energy. Okay, now we'll try to find out some analogy. I'll just write down the equations of motion for mechanical system. Look, we know m d2 x, this is the original equation. Okay, I'll just bring from beginning. So F is equal to m into a. Okay, F is what? F is minus kx m, and I write this is d2 x by dt square. Okay, so if you want to write this like this, you will get minus k by m into x. You bring it left hand side, all of them. So what is the final equation you get? You will get d2 x by dt square plus k by m into x is equal to 0, right? Okay, so now this this k by m has been taken as omega 0 square. Okay, so k by m in the mechanical system is taken as omega 0 square. Now see, if I write the equation of motion what we know in our LC circuit, d2q by dt square plus q by c. Okay, I think there will be LC, q by LC is equal to 0. Now if we compare these two equations, we will get to know some quantities like electrical analog of quantities, like say I can see, as we have seen. So the mass is analogous. So in the mechanical system, what is mass is inductance, self inductance in case of electrical circuit. Okay, because it was here L d2q by dt square. I'll write like this. So this is kind of m, it is acting as m. So that's why this self inductance, it is called electrical inertia. Electrical inertia. So this is called electrical inertia, as the mass is inertia for mechanical system. So this is electrical inertia for electric circuit. That means what? It will oppose the current in the circuit. Self inductance, as you know, it will be creating opposite. So this is actually, it will give back EMF. So that's why it is opposing the current, change in the current in the circuit. So that's why it is acting as inertia. So this is called electrical inertia in electric circuit. So why it is called inertia? Because it opposes the change in the current in circuit. Okay, change in the current in circuit. So that's why, as you know, mechanical system, m actually, m opposes the motion, okay, or opposes the velocity, I can say, change in its states. In a very precise language, m is the inertia which opposes the change of its state of motion or rest. Now look, if we compare these two equations, see 1 by c is actually equivalent to k. K is the spring constant in mechanical system, which is actually analogous to reciprocal of the capacitance. Reciprocal of the capacitance, okay? This is analogous. So electric analog of, sorry, mechanical analog of spring constant in the circuit. Okay? Now displacement, you can see it is very much visible that displacement in the mechanical system is analogous to the electric charge in the electric circuit. So this is analogous to, so displacement is analogous to the charge. So hence, if the displacement is analogous to charge, then dq dt must be analogous to dx dt, which is velocity in the circuit. So velocity, so and this is actually current. So current in the circuit, electric circuit, is analogous to the velocity in the mechanical system. Okay. Now see, in the mechanical system, the total energy can be kinetic energy, and it can be it can be sum of kinetic energy and potential energy, so half kx square, that is the spring potential energy for a spring mass system, and half mv square, this is the kinetic energy, as I already discussed. And in case of electric circuit, there will be two energies in the LC circuits. There is one is electrostatic potential energy, which is given by q square by 2c, and the other one is the magnetic energy, which is given by half L I square. You look here, see, this is analogous to kinetic energy, half m v square. So V is analogous to current, m is analogous to L, half is anyway, both are same. So see, the kinetic energy is analogous to magnetic energy, and electrostatic potential energy is analogous to the spring potential energy. Okay, so these were the analogies between electric circuit and mechanical circuit. So sometime you may be asked in multiple choice type question. So Q, X, L and C, which among these four is called electric inertia or electrical inertia? So then you have to write that L is called electrical inertia. And what is magnetic energy is analogous to in mechanical system. So kinetic energy is analogous to magnetic energy in electrical circuit. Okay. Now there are certain drawbacks. So one drawback is that we have taken capacitor and inductor circuit. So we have taken this as ideal, and inductor also we have taken ideal inductor, which has only capacitance self inductance, and it has only capacitance. But in real situation, there will be some resistance. Okay, some resistance will be there in real situation. So in that case, this LC oscillation will not be a perpetual, will not continue forever. Okay, because R will give some damping. So because of damping or resistive force, the oscillation will be stopped after certain interval of time. One more point is that, as I said, there is some resistance associated with inductor always, and even sometime in the capacitor, with the capacitor. See, we have taken ideally the total energy is the sum of electrostatic potential energy and magnetic energy. We have taken this thing in case of ideal situation. But since this inductor had some resistance, there will be power dissipation, and due to dissipation, this total energy will not be exactly equal to these two energies, sum of these two energy. It will be less actually. It will be less than the sum of these two energy. Okay, so this energy will be actually less than this total energy, because some of the energy will be dissipated energy. Okay, dissipated as joule heat. Okay, joule heat. So that dissipation, if you add with this electrostatic energy and magnetic energy, then you will get the whole energy will be equal to, or sum of these three energy will be equal to the total energy with what you started the experiment. That is the initial energy of the circuit. Okay, so thus we have completed this topic, LC oscillations. If you have any specific questions, I think Guna Selvi, you are there, and Deepa, if you have any doubt, any question, anything, you can ask me now. This is now open for discussion. Do you have any doubt? Deepa, do you have any doubt? Whatever so far we have discussed?
No, sir, no doubt.
No. Okay. Deepa said no. Uh, Guna, if you can answer me, it will be better for me to understand whether you have understood or not. Okay. So since I am not getting any response from you, Guna, I'll consider that you have understood. If you have not understood anything, just go back and listen the lecture again and read your textbook, NCERT textbook. If you don't understand further, you can ask me in any class regarding this. Okay, so we'll stop it here. Okay, bye for today.